Okay, in this lecture, we continue to study the linear homogeneous ordinary differential equations with constant coefficients. Recall that an equation, a linear equation, may be written in the operator form as L of dy 0, so because we have a homogeneous ODE, where L of d is formally a polynomial of degree n in the derivative operator with respect to t, right? And a1, an minus 1, an are the constant real coefficients of the nth order homogeneous linear ODE. Recall that we propose a solution like this, e to power lambda t, where lambda is a constant to be determined, maybe real or complex. And if this is a solution, okay, it must satisfy, the equation must be satisfied upon substitution. So taking the derivative of this function up to order n and substitute into the equation, we see that the equation L of dy, okay, takes the form e to power lambda t, L of lambda, which must be 0 for e to power lambda t to be indeed a solution, right? Which implies that because e to power lambda t is never 0, this implies that L of lambda, okay, explicitly written lambda to power n, a1 lambda to power n minus 1, a n minus 1 lambda plus a n must be 0, okay? What we call it characteristic equation of the differential equation. So as you see, as you remember, the problem of solving a homogeneous ODE, linear ODE with constant coefficient has been reduced to finding the roots of these so-called characteristic equation. Okay? And in the previous lecture, we talk about that. We say that we talk about some general results, very well known about the roots of such a polynomial equation of degree n. To sum up, we expect totally n roots. These roots may be real or complex roots. Real or complex root may be single or repeated roots. What else? If this characteristic equation has a complex root, then the complex conjugate of that number is also a root, so that complex roots appears in pair. These are very well known. So let us discuss these cases in detail. Okay. So as you remember, as you understand, there is a first case where the roots of the characteristic equation are real. So let's say real distinct roots. Okay, so let lambda, say lambda 1, okay, is a specific number, be a real and distinct root. root of L lambda equal to 0. Okay? That is, what does it mean? That is, L lambda 1 is indeed 0. Okay? And L of d e to power lambda 1 t, look at that, when we substitute y e to power lambda 1 t into the equation is satisfied, telling us that one solution of the ODE is e to power lambda 1 t, okay, with real lambda 1.
What do we mean by distinct?
There is no any other root equal to lambda 1, okay? Because we have totally n roots. Good. So now look, in particular, assume that all n roots are real. Assume that all the roots of L lambda equal to 0 are real and distinct. That is, look, there are totally n roots. We have lambda 1, lambda 2, lambda I, lambda j, and finally lambda n are all real. Good. With this, such that lambda I is not equal to lambda j when I is not equal to j. This means that the roots are distinct. Okay. Now, in this case, the required, remember from the general theory that to find the general solution, we need to determine n linearly independent solutions. Okay? This solution e to power lambda 1 corresponding to one root of the characteristic equation describes only or gives us only one single solution, but we need n solutions. In this case, under the assumption that all the roots are real and distinct, okay, the required solutions or n solutions are e to power lambda 1t, e to power lambda 2t, and finally e to power lambda nt. Okay? Where lambda I are all real. Good? And hence, and the general solution of our equation, which is the homogeneous ODE with constant coefficients, homogeneous linear nth order ODE, is of the form y of t C1. Remember from the linearity that if e to power lambda 1t is a solution, then any constant multiple of that function is also a solution of the homogeneous equation. So we introduce the linear combination constant C1, C2, Cn and write the general solution we require or suggested by the general theory in the form lambda 2t plus Cn e to power lambda nt, where C1, C2, Cn are arbitrary linear combination constants. Okay. Furthermore, it is possible to see that such solutions are linearly independent. Okay? So look, furthermore, two exponential functions are linearly independent. That is, look, say, Wronski determinant of e to power lambda it and e to power lambda jt. Consider the Wronski determinant of two exponential functions with exponents lambda it and lambda jt. By definition, we have this determinant e to power lambda it, e to power lambda jt, and on the second row we have lambda I e to power lambda it, lambda j e to power lambda jt, and calculating this determinant we have lambda j minus lambda I e to power lambda I plus lambda j times t, which is clearly non-zero whenever I is not equal to j. Okay? So two exponential functions appearing in the general solution of the equation are linearly independent, provided that lambda I is not equal to lambda j. Okay, so this is the first simplest case where all the roots of the characteristic equation are real and distinct. Here are some specific examples. Look, for example, let's find, to be specific, let's consider specific ODEs. First, let us consider a second order ODE. Example, find the general solution of y double prime plus 2y prime minus 3y equal to 0. Okay?
General solution.
Yes. When we talk about the solution, we mean general solution. Okay? So look, actually, let's write this equation step by step, or we have this d squared y dt squared, good, y double prime is this, plus 2 dy dt. To write down the operator form, we use in principle or hiddenly these steps that I derive for the first time. So then this may be written as d squared dt squared plus 2 d dt minus 3 y equal to 0. Okay, And recall that by d, we denote the derivative operator with respect to t. So the equation takes the form 2d minus 3y equal to 0. So as you see, this is nothing but L of d, okay? The differential operator, L of dy is 0. So this is the equation written in. So this is L of d. Okay, so characteristic equation is nothing but can be obtained from L of d on replacing d, operator d, by number lambda. So characteristic equation is L of lambda equal to 0, or explicitly it is lambda squared plus 2 lambda minus 3 equal to 0, and which may be written as, look, it is not difficult in this case to see that the two roots are 1 and minus 3 respectively. So the left-hand side, that is characteristic polynomial. The polynomial on the left-hand side, yes, we call the polynomial on the left-hand side as the characteristic polynomial of the differential operator. So the characteristic polynomial may be factorized in this way. So to give two real and distinct roots, lambda 1 is 1, lambda 2 is minus 3. Okay? And therefore, corresponding to lambda 1, so corresponding to lambda 1, so what does it mean? When lambda is lambda 1 or 1, actually the proposed solution e to power lambda t, do not forget, we always propose a solution of this type when we deal with an equation, homogeneous equation with constant coefficients. So we are looking for a solution of this type, and the problem is to find the lambda, okay, making this proposed form indeed a solution. And we see that 1 lambda is 1. So when lambda is 1, so a first solution is e to power 1 lambda 1t, okay, so e to power t. And there is another possibility. If lambda is minus 3, okay, this function stands for another solution. So e to power minus 3t is also a solution. So clearly they are linearly independent. So this form, this set, to be formal, you can say that e to power t and e to power minus 3t is a fundamental set of solutions, which means that they are the solution of or elements of this set of functions, okay, are homogeneous solutions of the differential equation, second order differential equation under consideration, and they are linearly independent. Then the general solution is the linear combination of that. Good? Now, let's see, actually they are independent, we know, but let us recall some previous theorems and formulas we learned in this lecture. What about the Wronski determinant if we use Abel's formula? Remember, look, this is y double prime, second order ODE plus a1, the general form y prime, plus a2 y is 0. Okay? So this is a second order homogeneous linear ODE with two constant coefficients. And recall that from Abel's formula, it is known that the Wronski determinant of the solution should be of the form. The Wronski determinant of solutions should be of the form e to some constant, e to power minus a1 dt. Yes, a1 is 2 in this case, the coefficients of y prime. Okay? For a second order ODE, so it must be 2, so minus 2t. And for a linearly independent pair of two solutions, we have to find C, which is non-zero. Actually, look, indeed, now we have explicitly the two solutions, so we can verify that the form suggested by the Abel's formula is indeed true. Actually, look, let's find the Wronski determinant of the two solutions, e to power t, e to power minus 3t. We have e to power t, e to power minus 3t. We have to calculate this determinant, minus 3 times e to power minus 3t. Okay? Calculating this determinant, we have minus 3 times e to power minus 3t times e to power t minus e to power minus 3t e to power t, which can be written as minus 3 e to power minus 2t minus 1 e to power minus 2t. So we have minus 4 e to power minus 2t. So as you remember, as you see, the calculated Wronski determinant for the two solutions we obtain explicitly agree with the form of the Wronski determinant suggested by the Abel's formula with C minus 4. Okay? So as you see, comparing with the Abel's formula, we see that for these two linearly independent solutions, the constant C in the Abel's formula is minus 4. And if it is non-zero, it says that the two solutions under consideration are indeed linearly independent. Okay. Here is another example. For this case, look, one more. Solve this. Y double prime minus 4y equal to 0. So obviously we can write the equation d squared, second derivative term, y minus 4y equal to 0. So L of d, the operator, differential operator in this case is d squared minus 4. And the characteristic equation is lambda squared minus 4 equal to 0, giving the two roots plus or minus 2. Okay? And therefore, the first solution is e to power 2t, and the second solution is e to power minus 2t, and therefore the general solution we require is c1 e to power 2t c to e to power minus t. Good. In this case, let's check again Abel's formula. Abel's formula tells us that omega is e to power, look, the coefficient of y prime is 0 in this case. So in this case, a1 is 0. Good. In the second order ODE. So we have 0. Integral of a1 is 0. Therefore, the Wronski determinant, the Abel formula tells us that the two solutions has a Wronski determinant, which is a sum constant. For independence, we must have a non-zero constant. Actually, indeed, look, the Wronski determinant of e to power 2t and e to power minus 2t is e to power 2t, e to power minus 2t, 2 times e to power 2t minus 2 times this. And we have multiplying e to power 2t and e to power minus 2t. We have e to power 0, which is unity. So we have minus 2, so minus 4. Good. So C is minus 4, suggested by Abel's formula. Okay. Anyway. Good. Now, let's come to a second case where the roots are complex and which appear in pairs. So let's say case 2. Case 2. Now we deal with the case where the characteristic equation has a complex root. Complex root. Now, let lambda, okay? Do not forget we propose a solution of the type e to power lambda t, okay? Let lambda a plus or minus I be, good, be a pair, and we know that complex roots appear in pair. So be a pair of complex roots. Complex roots of the characteristic equation and lambda equal to 0, where, be careful, where A is real, B is real. Real and imaginary parts of a complex number are both real. And I stands for the complex unit. So I squared is minus 1. Good? Now, of course, these cases may be stated as theorems. Okay? So according to this theorem, okay, we suggest that, or we claim that then look, we have two roots, so we have to generate two solutions corresponding to such a pair of complex roots. Good? And since the characteristic equation has totally n roots, we finally generate n roots to form a fundamental set of solutions. Okay? So then I'm saying that we claim that the two solutions of the ODE. What is the ODE? Linear homogeneous ODE with constant coefficient, which is in this form, corresponding to such a pair of complex roots are given by e to power, let's say y1. First solution is e to power at times cos bt, and y2 at e to power at sine bt. Okay, so which are, look, obviously the root of the characteristic equation is complex, but we generate two real functions of the real argument t, which are functions of the real argument or real variable t. Okay? Remember, a is a real number, so e to power at is a real function. Okay, cos bt, b is a real number. It is the imaginary part of the complex root. So two solutions corresponding to two roots, which are complex conjugate of one another, are expressible in terms of exponentials and basic trigonometric functions or circular functions, right? So to prove this, that this is indeed true, look, in this case, which case? In the case where the characteristic equation has a root like that. In this case, the characteristic polynomial L of lambda, okay, contains a factor. Lambda squared, or lambda plus a lambda minus a squared plus b squared. Isn't it? So L of lambda should contain a factor like this. So if this factor is equated to 0, good, so that when this factor is equated to 0, to make L of lambda 0, so if a quantity which is the product of several factors is 0, as you remember, if one factor is 0, then the quantity becomes 0. So equate this factor to 0, we find that lambda minus a squared is minus b squared. and b squared is real, so minus b squared is a negative quantity. So that taking the square root of both sides, we have lambda minus a plus or minus ib, good, and which implies the two roots a plus or minus ib as suggested. Good. So L of lambda contains such a factor, obviously. Hence, remember, L of lambda is nothing but it is derived directly from the differential operator L of t on replacing d by lambda. So, hence, L of lambda, L of d, okay, the differential operator has the same factor or contains the same factor. Has the same factor of that d minus a squared plus b squared. Good. And the ODE and our ODE may be written as, look, our ODE is that L of dy is 0. Now, L of d contains a factor like that, so we can write it as T of d. So extracting this factor, d minus a squared plus b squared. So the composition of L of d. L of d is an operator. Formally, it is a polynomial of degree n. So here is a second degree polynomial as a factor, as one factor. So T of d is still a polynomial in d of degree n minus 2. Good. So T of d is unnecessary to find it explicitly, but we have this, our equation, and T of d is a linear operator in the form of a polynomial in d, but the degree is n minus 2. Okay? Where T of d is a differential operator polynomial type of the same type as L of d is a differential operator of degree n minus 2. Okay? Anyway, so if this is the case, we'll see that our nth order ODE should have a solution which satisfies this second order ODE. Good. Therefore, from this equation, look, let's write the ODE explicitly. Now, a solution must be the solution of this second order equation. And therefore, we have, from that, we have this ODE written explicitly, d squared minus 2ad plus a squared plus b squared y 0. Okay. Which has solutions, or written in the prime notation, minus 2ay double prime plus a squared plus b squared y is 0. So two solutions of our equation of order n are also solutions of this second order ODE. Okay. So which has a solution. And we know that if lambda is this one, because remember, we propose a solution like this. Solution e to power lambda t. So, and lambda is a root of the characteristic equation, and we see that lambda in this case is e to power a plus minus I b t. So this is a solution. But what is the problem? The problem is that, as you see with lambda complex, we get a complex valued function of the real variable t. But our objective in this lecture is to find real valued solutions for our differential equations under consideration. So the question is whether it is possible or not to define two real valued solutions of the real variable t. Okay? And our hypothesis, and we claim that actually the two real valued solutions have this form, these forms. Now we try to prove this. Okay? Now, so which has a solution like that, y of t e to power a plus or minus I b t, which is a complex valued function of the real variable t. Okay? Now, this solution may be written as that. Look, we have e to power at, good, times e to power plus or minus bt, ibt. Correct? So there is no problem with the first factor. E to power at is a real valued function of the real variable t. But the second one can be written as e to power at times cosine plus or minus bt plus I sine plus or minus bt on using the very well-known Euler identity. Euler identity, which is that e to power a theta is cosine theta plus I sine theta. As you remember here, e to power plus or minus I bt, you can think that theta is plus or minus bt. Okay? So we have plus or minus bt as the argument of cosine and the argument or sine. But this solution, okay, look, So y of t is this, e to power at. Remember that cosine is an even function. So cosine plus bt or cosine minus bt are identical. So we have e to power at times cosine bt plus e to power at. Look, but sine is an odd function. So sine plus bt is sine plus bt, but sine minus bt is minus 1 times sine bt. Therefore, we have here plus or minus sine. So plus or minus I times e to power at sine bt. Yes? So this complex valued function may be written as a function, say u of t plus or minus I times v of t. Good. So u of t plus or minus I v of t, where u of t and v of t are real valued functions of the real argument. Okay? And this is a solution of our second order ODE. And please be careful. If this is a solution, okay, this is a solution and satisfies the ODE so that, look, taking u double prime, take the derivative of that, u double prime plus or minus I v double prime. So second derivative of that, plus or minus 2a y prime. So u prime plus or minus I v prime plus a squared plus b squared y. So y is of the form u plus or minus I v is 0 because it is a solution. Remember that when we have a complex valued function, taking the derivative means we take the derivative of real and imaginary parts respectively. So writing real and imaginary parts of the left hand side, we have this u double prime, okay? Minus 2a u prime, this term, plus a squared plus b squared u, this term. This is the real part of the left hand side, plus or minus, good, I, and this is the imaginary part, this term, proportional to the complex unit, v double prime, minus 2v prime, plus a squared plus b squared, v, 2a, v prime, okay, which must be 0. Good. I collect the imaginary parts. So what is known? If a complex quantity, so we have a complex quantity on the left, which must be 0. A complex quantity is 0 if and only if its real and imaginary parts are both 0. Good? So this is the real part, must be 0. This is the imaginary part, must be 0. Okay? For a complex quantity to be 0. Now, what is the meaning of that? U double prime minus 2a u prime plus a squared plus b squared. U is 0. Look, this is nothing. but our differential equation where y is replaced by u. So u is a solution. And look at that. This is our differential equation where y is replaced by v. And the result is 0. So v, the function when y is taken as v, upon substitution gives us 0. So it is a solution. Okay? So both u and v are solutions. What is u? U is e to power at cos bt. And what is v? E to power at sin bt. Okay? They are both real, which is the statement of our theorem. Okay? So as you see, we find that both u and v are solutions, which completes the proof. That is, both u, which is e to power at cos bt, and v, e to power bt, e to power at sin bt are solutions which completes the proof. Remember, u is nothing but y1. V is nothing but y2. Okay? It is not difficult to show that the two solutions are linearly independent by taking their Wronski determinant. So we get a function, or we get two solutions which are independent. It is straightforward, say, to show that they are linearly independent. Okay? So we have shown that if a differential equation of order n has a pair of complex roots with real part A and with imaginary part B, okay, then the two solutions corresponding to such a complex root are trigonometric functions weighted by exponential. Cosine bt, sin bt. B is the imaginary part of the root, and in the exponential factor, A is the real part of the complex root. Good? Here is an example. So let's say, as a result, you may say that as a result, the corresponding part the part of the general solution corresponding to such a complex pair of two solutions, the corresponding part of the general solution is of the form e to power at c1 cos t cos bt plus c2 sin bt. Right? Where c1 and c2 are arbitrary constants. This is the part of the general solution corresponding to a pair of complex roots. Here is an example. Look, y double prime minus plus 9y is 0. Let us consider this simple case. We have immediately d squared plus 9y is 0. So our differential operator is d squared plus 9. Hence, characteristic equation is lambda squared minus plus 9 equal to 0, or lambda squared is 9 minus 9. So lambda 1, 2, okay, is clearly a pure complex number plus or minus 3i. Okay? Do not forget I squared is minus 1. So taking the square, we get minus 9. So pure complex. So what I mean, in the general formula, general complex, comparing with a general complex number, we see that the real part is 0 and b is 3. Good. We have already plus or minus I, so b is 3. Good. Not minus 1 minus and plus 3. It is simply 3. Good. Comparing with that case. Therefore, the two solutions are, let's write fundamental set of solution is e to power 0 is 1. So we have just, let's write e to power 0t cosine 3t and e to power 0t sine 3t. E to power 0t is unity. So simply the fundamental set of solutions cos 3t and sine 3t. It is easy to see that they are linearly independent. Then this is the fundamental set, and the general solution in this case, because we have a second order equation, finding two independent solutions is enough. So we have look y of t c1 cos 3t, c2 sine 3t. So if you are interested, you may find the Abel's formula. Abel's formula, look again, y prime does not appear. So the coefficient of first derivative term is 0. So Abel formula suggests that omega must be some constant. Okay? A1 is 0 in the general equation. Abel's formula tells us that is a constant. Actually, you will see that the determinant of that cosine 3t, sine 3t, minus 3 sine 3t. So the Wronski determinant of the two solution. So 3 cosine 3t is 3 cos squared 3t minus plus 3 sine squared 3t, and clearly cos squared plus sine squared is 1, so we have 6, which is a constant, okay? And agree with the formula suggested by the Abel's theorem. It's okay?
3 times cosine squared plus sine squared. 3 times 1 equals equals 3.
3, yeah, not 6. Sorry. 3 times cos plus sin. So, thank you.